Okay, hello everyone, welcome. We are live for today's talk of CEDIM, organized by the Industrial Design Department. Today we are going to talk about the topic of informed matter, a Codeit research project started in 2015 and which focuses on exploration of additive fabrication processes. The talk will last 1 hour, and the last 15 minutes will be left for questions and answers. So please write your questions through section Q&A. We are in company of Andrea Graziano. Andrea is an architect and computational designer, member of and co-founder of Codeit, Computational Design Italy, currently engaged in teaching international workshops about computational design, digital tools, and robotic fabrication and architectural design, lecturing, and consultancy work. Andrea is a member and co-founder of STEAM Plus Lab, former Digifab Touring, a research cluster focused on digital fabrication, computation, robotics, and material research applied in the field of architecture, design, and art. Andrea acts as an active catalyst through his intense activity of social networking, of the paradigm shift in the fields of architectural research, computation, and science. A digital explorer, a nomad aiming to research, create, and envision the rapid evolution of science, technology, art, and philosophy, their possible convergence and tooling into design and architecture. Welcome, Andrea.
Thank you very much. First, thank you for the invitation. I'm really happy to have the chance to share part of the work that I did in the last years. So I think the best way to start is just go with the first slide. As George said, I'm a co-founder of Codeit. Codeit is a hub of people that have a common interest and strong interest in computation as a design medium in creative disciplines. We are really looking at all the possible way to use and to evaluate fields through the lenses of computation. So we are ranging from biology, neuroscience, architecture, design, and so on. We started Codeit in 2010 officially with other two colleagues, Alessio Rioli and Davide De Giudice, and through the years we started to involve other persons that became members or collaborators and so on. What we do usually is in first research. This is our main interest because without research it's very hard to move into consultancies and education and so on. So research is our first goal, and we have different topics that through the years we touch and we are still exploring. Informed matter is the one that I will show you today. Then we are interested to multi-agent strategies, biocomputation, brain-computer interfaces, and last but not least, artificial intelligence since a very long time. In the meantime, we are doing consultancies, and I'm quite proud by the fact that through the years, because we work as Codeit since more than 1 decade, we get in touch with some interesting companies like DuPont, with Haier, that is one of the main actors in China for home appliances. D1 is one of the biggest architectural engineering studios all over the world, and Comau is a robotic brand, robotic industry in Italy, and so on. Then we are doing a lot of education. Since 2010, we did more than 300 workshops all over the world. And we really think that education is a key point of any kind of activity. Without research and education, it's very hard to, let's say, to figure out how we can move and try to evolve our scenario. One of the other features that is very is defining really Codeit is the fact that we are working just on projects where we can go to the one-to-one scale and we can use digital fabrication tool. Usually our work is not just about printing something or creating some fancy shapes, but it's also about creating the pipeline through the digital tools to the physical one, creating the software in order to move the machine, and so on. And in the last year, since 2015, I had the chance, we had the chance to work also in robotics. We start as everyone literally from scratch, but in few, let's say, in few months, we started to develop our own software to move robots, and then actually we are collaborating with Comau. I told you, is a robotic company in Italy, a very big one, and we are literally writing with them software in order to move the robots. So this is a very short introduction to describe what Codeit does usually, but today I wanted to frame the lecture in around a very specific topic, that is its informed matter. And I want to start from a slide that I literally took from a Yoshihito keynote speech that he did several years ago when he was the director at MIT Media Lab. And the lecture title was Why Bio is the New Digital. And at some point, he was specifying that the future of the design will be shaped by 4 different, let's say, area of exploration. Computational design first, then additive manufacturing, materials engineering, and synthetic biology. And at that point, it was 7 years ago, if I'm not wrong, I started to think that more or less I was already involved in all of them. And so in some way, I was already very lucky. And maybe synthetic biology, it was something quite new, but in time we went in touch with different biologists and we started to be involved in different projects. And in time, through the time, I also started to think that one area of expertise was missing, because at some point you have to fabricate stuff, and additive manufacturing is fine, but then anyway you have to, at some point, to design the machine you will need in order to do something. And so robot and machines should be part of this diagram. I want to start from an image of a piece made by Neri Oxman at MIT from a collection that she exhibited in Paris some years ago. And in this image, it's very important because we can see something very peculiar to the new technologies that we can use in the last year. In nature, everything grows to create the various functions, including information inside the layer. And that's exactly what happened also in this object. In this object, there are 3 layers of information in order to create the object in itself, to fabricate the object. The first one, obviously, is the position of the material. A G-code file will deliver some instruction in order to release the material in some specific positions, okay? But under this layer, there is another one that you can see is the color of the material. So there is another layer of information that will define the color of the material through the different session. And then there is another layer of information that is about the stiffness of the material. The white is soft and the black is rigid, or maybe the opposite, I don't remember. Anyway, another layer of information allows the designer to define the physical properties of the object. So the way we can use additive manufacturing tools and protocols allow us to start to embed different series of information. So different layer of information will define the physical properties of the final object. And then, since then, designers started to take advantage of this kind of ability that those technologies allow. And as you can see, this is a very famous 3D printed chair made by Zadid architects in London. And what you can see basically is the result of the ability of the designer to deliver different quantities, different densities of material through the design shape, the chair shape. So as you can see, the blue parts are the stiff one, and the white one are perforated. So let's say are a sort of light use of the material. So we can start to deliver the material in very specific areas in this specific project. Through the use of topological optimization, the final design is heavily affected by the need of release material just in some portion in order to have a proper chair. So we started in 2015 officially, but the research started in 2013 with some experiments that we did in a very unconscious way at the time. A result that we called informed matter, just because we think that informing let's say the system that we create in order to produce the object allow us to do something very specific that it's very hard to do different. So the informed matter research project focuses on the exploration of additive fabrication processes. I mean to inform as to give form, as in to produce form to morphogenetic properties and capacities of matter by embedding information structure, further information structure during the fabrication process. And one of the key features of the research is to go beyond the current state of prototyping, according to which the physical prototype should be as close as possible to a clone of its digital counterpart, thus making fabrication a purely replicational phase. So everyone still today is judging the results of a 3D printing process through the ability to replicate as close as possible the digital artifact. And I think this is something misleading because it closes so many doors and opportunities in terms of exploration of materials. So let's start from the very beginning. This is one of our first 3D printed tests that we did in 2013. And the original file was a cylinder. So the point is, if we judge this test by its similarity to the digital file, to the digital prototype, this is a huge failure. It doesn't count anything. But at the time, we saw in this failure something very important. The material reacted to the instability, provoking something that is very peculiar to the clay material. It started to do those wheels and those circles and so on. Why? Basically, the layers fall down, and so the material has more space in order to be released. And so, if you understand which is the set, or let's say the framework, why this accident happened, you can start to think to replicate it. So, if you have a system, as we had, made of a robotic arm, a specific material, an end effector that basically is the tool that you use in order to embed or to transform information into something, and then you have the code that in some way is the link through all the actors, you can start to work on that very efficiently. We work at very different scale with different robots, and I want to start from the clay material. Basically, we work with different materials to 4 years of research that we did. We work with clay, with biomaterials, with polymers, with flexibles, and so on. Starting with clay, the first thing that I want to say, and this is one of the main critiques that we got usually from the designer and architects too, less from the industry or the artisan as well. We are not thinking to replace with robots anyone. On the very contrary, the skills of the person that are working with clay every day, so the ceramist, artisan, the people that really knows the material very well, are essential. Every time we were running the robot in order to 3D print clay, we need at least 4 person. Robotics guy, the computational design one, the ceramist, and then so on. So this is something very important. Then I told you, if you judge this object by the similarity to the digital file, is a mistake. But if you learn which are the set of, let's say, the framework that provide the error, you can start to organize those kind of errors. In this test that we did a few days after, we started to change the speed of the robots during the deposition. The flux of material was constant, but if you change the speed, basically you allow the material, you started to release the material at different speed. So the material in some parts should organize itself differently from other parts where the speed was increased. So you can, with information that basically are the speed of the robot, you can start to inform the matter. And when you start to run those kind of tests and get feedbacks and acquire sensibility, you started to use those kind of tools as a designer, basically, because you started to understand how to manipulate the set of information in order to provoke stuff. And also you can start to range from very organic effects. The middle image, you have an effect where the clay seems knitted literally by a machine. Then you have mistakes and so on. And then you started to understand the material better. And so here, for instance, there is the same nozzle releasing the material on a circle, but the nozzle has a cut, and so the angle between the nozzle and the circle is changing all around, and so the effects of the clay are very different. And so you started to understand the importance of the inclination of the nozzle and the release of the material. And then, obviously, in order to do all this kind of experiment, you at that time and still now, there is no plugin for the brand of robots that we were using. So basically, we started to build our own software. And just to give you an example, in order to run a robot in Italy, you need a certification, a license. We did the course, and at the end of the course, as a, let's say, proof of our ability, basically, we already sketch a first sketch of a tool in order to control the robot. And also the company itself was super surprised to see someone that was able in such a small amount of time to develop a tool in order to control their robot. And so this is more or less the first platform that we have. But the most important part of this image is this green and red series of points. They are not points, those are direction, but basically the designer, or at least we were literally not designing the object that we want to 3D print, but we were designing literally just the set of information that the robot wants, because robot wants just a point, orientation, and speed. And so you don't need to design any 3D object in order to define an object in itself. And this is something very important. Then we started to develop a simulation tool, a material simulation tool as well. And then we started to create our own software in order to run our own robot according to our needs. So every time you have a very specific need, you start to develop your code. And then we started to share our code with some companies and so on. But that's the point. As a designer and architect, I'm always very surprised when we are using tools in a non-very effective way. If a robot wants just points and orientation, why we need to design the 3D object? We did several workshops with a lot of students. We ran more or less 10 workshops during this experimentation, just to test if designer in few days could start to design the information instead of the 3D object. So they started to run a process where they design the information, they code the information for the robot, they execute the code, they 3D print the material, they evaluate the physical and aesthetic material properties, they reinforce, because every time it happens something specific, they reinforce the sensibility in terms of use of information, and then they can again design directly the physical and aesthetic material properties through a new set of information. And when you do that for days, you started to acquire a very specific sensibility, both in terms of information, robotics, and material properties. And these make you, in some way, an artisan, because your sensibility is different from the sensibility of your colleague. So we started to run clay printing in 6 axes, and play with clay printing 6 axes is completely different from 2D axis, because you are using the material in a very different way in terms of physical forces. So also the results when you bake the clay, it's more resistant eventually, and so on. And then we started to test with students. We had a lot of students during the workshop, different possibilities, and to work with the artisan. And one of the main interesting things that happened at the time is that sometimes it was very hard to explain to designer what it could be done with this kind of processes. But when we met artists and artisans, or ceramists, or people involved into clay in some way, they always more or less got immediately the point, what could be really done. So we started a lot of collaboration with people working in the clay. So for instance, here there is just some trajectories. So the information is the Z level, but as you can see, the nozzle pushed the material down. And so the final shape will be literally driven by the nozzle moving in Z. And these sort of things can't be designed on the digital tool, because the final result is the result of the physical, the materiality of the clay with the information. Those were some tests in order to check the clay reaction to the speed. As you can see, each line has a different speed, and the number of waves and the regularity of the waves of clay is something that super precise. The material react in a very precise way. So just adjusting the speed, you can start to modulate the material reaction. And this is something super interesting. And then in 3 years, basically, we always print cylinders, but as you can see, the effect driven by the set of different information to the final object are completely different. And at the end of the 3 years, we will called by Elettronica in Linz to exhibit our processes, because at the time that year the main topic was errors, and in some way those kind of results were the fact that information are changing the digital prototypes. And then we started to 3D print for some, let's say, brands. And this is an experiment that we did in order to relate with industry. And we developed an algorithm that is very well known. So we just embed it in our tool. It's called reaction diffusion. But what is really peculiar is that from the design of these 6 pieces that we have on the top and the let's say realization, the fabrication of them that you can see on the bottom, basically it took more or less 7 hours. And if you think those kind of art pieces, let's say clay pieces, are very hard to be done in the, let's say, traditional way that industries use. So when we start to talk with industry, they, let's say, realize that customization and the quality of the product could be something that really could give them a specific, let's say, a new set of opportunities. Those are the final pieces that we start to do. Those are some pieces that we did again for our Elettronica for the permanent exhibition, and so on. Then we jump into the polymers, and at the time they were PLA and ABS, but we were not interested in, let's say, FDM 3D printing, but something that at the time was called spatial 3D printing, basically how to release plastic materials in air. In order to do this kind of things, you have to inform the system with a huge amount of information, because when you release a material that is very hot at the room temperature and you want it stable, you have to have time to cool it down in order to keep the position. So, but the vertical segment need a specific time and a specific need, the diagonal need a specific time and speed, and then the speed and the time is different according if you're releasing in diagonal from the bottom to the top or the top to the bottom. So the number of information that you have to encode are quite challenging. Those are all the, let's say, possibilities or all the things that we were able to control in order to do something like that. And we started to 3D print. Keep in mind that it was in 2016, so before many other experiments that more or less were on the same page. This one 1.4 meter piece that we 3D printed in a couple of hours, let's say. And the weight obviously is super lightweight. It's around 300 grams, but the other things that is very important is that in order to release the specific set of information that you want to release to the material, you have to build your own tools. And you have to specify the information, and you have to be able to create the machine in order to transform the digital information in some physical effects with the material. So through the years, we did a lot of extruder, we did a lot of tests. Most of them are public. We have a GitHub page where they are published. And this is one of the tests that we did. As you can see, the material is super stable. Obviously, this is a speed up video 5 times. So, but the material is quite precise in the release. Obviously, it's a very small piece, so nothing super engaging. But anyway, just to show you the quality. And obviously, we have also to 3D print something in order to, let's say, pay the researcher, because all the experiments that we do are self-promoted in some way. Then we started to be interested because we saw a very specific experiment done at MIT. We started to experiment with the elastic materials. So basically, we were playing with PLA, so extruding PLA, on a pretensioned lycra textile. So as you can see, there is some black lycra that is already pretensioned, and we are 3D printing on it something. And when you release the material, so you let the two material coexist and find an equilibrium of forces, basically you shape the object. And according to the amount of material, to the direction of the material, to the forces that you have in the lycra, the object will be completely different. And those kind of things are super hard to be simulated on digital tools, very hard to be simulated. And so we started to play with those kind of things and to check literally through the experiment, you have the feedback in order to understand the material. And we did some workshop in order to expand the feedbacks and to let the students play, because it's also quite fun. As you can see, it's a very fast process. Few lines of material that are very fast and you get the object. So you can do many iterations in order to work. And at the end of the workshop, basically we take some days, just to, okay, what we learn from what we did. And we started to organize our feedbacks in something that could be 3D printed and has some meaning. And those are a series of pop-up lamps, basically. Some lamps that you can 3D print in a couple of minutes or 5 minutes, 10 minutes, according to the amount of material that you release. And then when you release the lycra, you get your 3D printed object. And obviously, this object could be washed several times, and it works always because the material is quite resistant, and the material melt literally to the fiber of the textile. So it's very, let's say, the adhesion between the two materials is very high. And then I want to move to another piece of research that we did, probably the most important, because it opens a lot of doors in some way. It's about biomaterials. As I told you at the beginning, the Joito slide about the 4 different areas of expertise needed for the future of design really got us in the direction of biomaterials and biology, and then synthetic biology. In 2000, sorry, why it doesn't move? Okay, in 2014, we met an Italian guy working in Amsterdam since years, and he was working with Mycelium. He is currently working a lot with Mycelium. He is a designer, biodesigner, let's say, working with myceliums. And we did a workshop with this guy, Maurizio Montati is the name, and a WASP company, because they were trying to develop a biomaterial 3D printer. And so we joined our forces in order to try to figure out something. And we were invited by the VAC Society in Amsterdam to do a workshop about those kind of topics. So basically, we did a workshop together. It wasn't exactly about mycelium. We were 3D printing organic material to let some living organism eat the material and develop some specific, let's say, growth path. But at the time, we started to discuss with Maurizio about something different, about a project that we called the BioXMAC, because it became, let's say, a spin-off of our informed matter research. And the BioXMAC project, basically, obviously, is a transdisciplinary project aiming to join computational design, biology growth, and additive fabrication and robotic protocols. So a sort of mixture. As you can see, we start to develop also in this specific case our own extruder in order to extrude the material, in order to control the pressure, the temperature, and so which is the peculiarity of the material. First, is a composite material made of basically cellulose. This is the bigger percentage of material of the composite. It's a very thin and sterilized cellulose. Then myceliums. So you have a living organism that is very small, is colonizing the material already, but it's a living entity. And then some natural gel made of seeds in order to create a sort of adhesion that give form to this sort of paste that we wanted to 3D print. And printing a natural living being is something super difficult, because you have to be very clean in all the possible way. Then the material, the cellulose has to be super clean, and then you have to do it in a very specific moment. If you have too much myceliums inside the material, it's not good. If you have a few, it's not good as well. So you have a very specific moment of the growth that you have to use. Here we are me and Maurizio mounting our extruder that obviously it's released on our GitHub page. We did several iterations every time, more or less. We were doing some experiments or changing the design, and those are let's say the parameters that we were trying to control in order to inform the material through the deposition. You can't see the video. I don't know why. Anyway, sorry guys. I'm very sorry that the video is working on my second monitor, but not in this one. Anyway, as I told you, 3D printing this kind of materials is something that you have to be very careful, because there is a moment that is the preparation growth. Basically, you have to colonize the cellulose with some myceliums that they started to grow. And then there is a specific moment where you have not too much. And then obviously, after you 3D print it, you have the final growth. And the 3D deposition is literally affected by the homogeneity of the material, the adhesion of the material, and the viscosity. And then obviously you have to keep the sterility and to avoid collapses and so on. But the most important part is that your material is changing through the time and is changing the final object as well. So those are some pictures took at the third day, the fourth, the fifth, and the seventh. And as you can see, the mycelium start to colonize the surface of this sort of compound that you have. And while eating the cellulose, they started to release those microfibers that are replacing the cellulose. And those microfibers started to be very solid, very stiff, and very light. Very. Those are the objects after a couple of weeks of, let's say, incubation. Then at some point you have to kill the myceliums, because you don't want them to grow infinitely. And those objects are super lightweight, super. They have this very peculiar aesthetic, because the surface is soft, but they are super strong. It's very hard to break them. Trust me, it's very hard. And they have their own aesthetic as well. So we started to work on how to create stable layers, because it was very hard to raise in height with those objects, because the material is very unstable. So as you can see here, you have some failures. And by failures, you learn, obviously. As you can see, the behavior of the material is very different from one example to the other. Then you have different viscosity, different adhesion. We did thousands of tests in order to start to work properly. Then you have those high pressure leak and so on. But if you started to learn and to get feedbacks and to reinforce your sensibility, you started to have the right receipt in order to 3D print and started to be very precise in 3D printing those kind of objects. Those are, let's say, the final test that we started to do. It's an ongoing research, so I would say that we never finish properly the research. But those are the final pieces. Obviously, they are very small, but they were quite important. Keep in mind that it was in 2017. Mycelium weren't on the edge as they are today, and we got some interest. The first one, there was in 2019, there was an exhibition in Paris named La Fabrique du Vivant, where more or less all the designers working with biomaterials, the most important one, were asked to exhibit their research, and we were super happy when they invited us to exhibit. As you can see, very old prototypes. They were already quite old. But this was the first step. And then the other one that really make us even more happy was the interest of the European Space Agency. Why? If you have to move and to go in space, what you should do or what you should care about is the weight of the material that you want to move and the volume. Weight and volume are the main voices when you need to calculate the budget. And if you have a material, basically, that weight a few grams, because mycelium with few grams you can colonize, if you have time, hundreds of kilos of cellulose. And you have a discarded material on the space station and in any space mission that is the cellulose, because at some point you have vegetables growing there, and then so you have discarded materials. So you can think about those kind of compound as a sort of holy grail, because with few grams you can start to have a very resistant object. And so our research that we did with Montalti started to be published inside of some European Space Agency papers. At the moment, we have 4 papers where our research is cited as a very interesting one. So I think that we are almost there. The entire set of slides and things that I said is just to say that informing matter. So basically, the ability of the designer or the architect or the engineer, whoever, to start to embed a layer of information through the additive manufacturing process is a key point. And the other key point is started to be aware that your digital artifact could be enriched by the material properties. So you can really start to think that what you design on the digital tool could be really enriched by the morphological properties of the process. And the third thing that to me is even more important is that during this specific phase, you can start to understand the material in a completely different way. I think that the set of feedbacks that we got in 3 years of research are very different from the feedbacks of the people that were using those kind of material before, because you're working with new tools with new lenses, I would say. So in 2009, Neil Leach said this the phrase that I still like, and I think it's a key point. We are moving after many years of digital predominance in architectural research to matter again, but in a very new way. We are moving to a new materialism era, and I'm really agree with him. If you are interested, all those experiments are published in a free publication. It's called ARM, and you can find easily online if you look for Codeit, or you go on our website, Codeit website, you look for ARM and you can download it for free. There are also several videos. And then more or less, that's all. So thank you.
Thank you very much, Andrea. It was incredible. Really impressive.
Thank you.
Several years of research, and well, you are even touching topics of going to space, or at least giving giving this outlook of where this technology could go.
Yep.
Before we start reading questions, and I invite everyone to start writing their doubts on the part of the messages, I think I would like to make a question that it's probably the most common for students. Is it's really interesting, but it's hard.
In which sense? There are very different on the side of the research, but
like how do I start? And isn't it's too difficult to learn? No, this is the first thought.
Maybe I'm really no, I not agree. I don't agree with you. I think that starting is the easy point, because you see something very different and sometimes very attractive. So, I really like it. So you have the energies, you have the enthusiasm, and so on. I think the difficult part starts when you need money, you need robots, you need time, you need the space. So all the very practical things that you need in order to do research. But I think do the first step. It's easy. It's easy because there are so many researchers all around the world. There are so many positions. It's easy to get in touch. It's easy to have a workshop all around the world that are in some way exploring these kind of things. Obviously, you need as well to move sometimes and so on. But I think that the first moment is where you have a lot of enthusiasm. And when you have enthusiasm, you can do something that it was impossible before. So I think that the most difficult part are the very practical one. Bureaucracy and these kind of things are slowing down any kind of research. And so, but anyway, for sure, is probably the most difficult part for a student, or at least for a person that started to face those kind of things, is to have a very, very, to have the ability to filter the huge amount of information there are around. Because when you talk about mycelium in design, there are so much stuff, so many experiments, so many people doing it, but filtering, maybe you need experience, or maybe you need something, some different criteria, but there are very different quality of research. And so the European Space Agency, from what you read sometimes on the usual magazines, is something, there is a huge gap in between.
We have a question about mycelium. They're saying, if you and your team harvest all the mycelium material,
Not personally, but Maurizio Montalti, that is the biodesigner, is collaborating in a university, and basically they growth so many different mycelium species because they do it for scientific interest, but they also select the myceliums according to the task that or what is required by the project, and so they have a huge amount of knowledge in terms of which kind of mycelium we should use. For instance, if you want to 3D print in space, anyway, you have a very limited amount of resources in terms of water, in terms of humidity. It's very hard to control huge, big spaces in order to create to grow a lot of material, and then you're working in microgravity. That is something completely different from what you could usually test here on our planet. So basically, we had the chance to test the receipt that we create in space, and one of the paper is exactly about that. So it's quite. We didn't harvest the mycelium, but that's why you have transdisciplinary teams, because someone knows how to do it very well in a very scientific way, in the right environment, in the right lab, and then we were using that material. So the material was traveling from Amsterdam to Italy all the time, let's say.
Incredible. Well, and if there is anyone else who has questions, you can also write it in Spanish, and I can translate. There is no problem. They're asking, so the kind of mycelium used in the 3D printer objects depends on the object qualities?
No, not really. No, not really. At the end, we test more or less 20 of them. We did it during a workshop with a lot of students, around 20 students, and we test a lot of them with different mix because it's a compound, so you can mix also the mycelium as well. And at the end of the workshop, we let the object grow for 3 weeks, and we started to select the best mix, so the best compounds, and then we did some other tests, but in the end we have a couple of mycelium that we are using for our purposes, let's say, not the space ones that are completely different.
And what can you say about the design criteria and the use of algorithms? Do you think it's limiting or it's expanding you the possibilities?
Maybe it's a research project. So in some way, the beginning of any research project has to be stick to a scientific criteria. So let's say creativity is not really the first ingredient of the process. For instance, all the clay tests that we did at the very beginning, and for more than 1 year, I would say, were cylinders. So design, let's say creativity wasn't there at all. But it's exactly why we were evaluating the different layer of information that were framing the different results, and then you get the feedbacks. And then when you have the feedbacks several times, thousands of times, you start to have a sensibility. And at that point, you started to use your creativity and start to use your skills in terms of design to start to organize something that is literally framed on your previous sensibility that you create through the scientific approach to the material. So there are different phases where you can balance, let's say, design and so on. But on the other side, computation is transversal. The entire research has a huge amount of computational skills and computational thinking attitude through all the research, from the very beginning to the very end. So I would say that computational thinking or computational design are the key ingredients that are constant through all the research.
Can you explain a little bit more about what is the computational thinking?
Yes. In the last couple of years, we started to fight literally with the common opinion that we have about computational design. Every time we say, oh, computational design is related to computers, to skills, tools, softwares. No, not at all. Computational thinking is something that is related to the way to solve or to frame something through a series of steps or instructions. Okay, there are a couple of papers that are super interesting, but Matteo Pasquinelli is an Italian guy, but he's teaching in, if I'm not wrong, in UK, where he shows that even in maybe Mexico, in the Mayan culture, there were some procedure in order to build stuff that were made by instruction. So you have to do that, that, and that in that way at that time. So you have protocols of instruction that are literally algorithm, but they were physical. There was someone that remembered the instruction because they were not written in first. They were rituals written literally to create stuff. And then you have people that are following the instruction and managing pieces of stuff in order to build something. Those are, let's call it them proto-algorithm, but to me they are algorithm. Then Gaudí, no computer at all, but computational thinking in first. There were literally set of instruction and procedure in order to obtain some simulation that were basically the ground, the framework in order to build amazing buildings. So computational thinking is, okay, I have a problem or I have a task, how I can define a set of instruction or a set of strategies in order to solve or frame it, okay? And you don't need a computer, you need a piece of paper, and you need you think about it, and then eventually, since we have computers, they could compute faster than us, they could compute more than us, they could be interconnected. That's a super huge advantage, but at the end, you need to program. So the computational thinking is behind that. And that's I know it's a very specific point of view, but I don't like the fact that the computational design is merely defined by, okay, you're working on the computers doing stuff. No, I don't like it. I am an architect by formation. I don't define myself an architect anymore. And when someone asks what you do, I'm a computational designer. In terms of computational design, I'm doing computation. Okay, so that's my job, and computation is not just about computers. It's about understanding problems and frame solution through the use of set of instruction. That's my point.
Wow. Okay. Well, incredible. And I have one last question. I don't know if someone wants to add a question.
I have time.
About industry, no, you say that it's another world when you connect to industry, but you also said you work with different brands. How is this part of the computational design? How relates? What is the product or the service which offers to a brand?
Let's start in that way. If you need to design something, the opportunities in terms of embed computational design strategies into any kind of industrial process are endless. Industry usually frame in very small boxes a lot of tasks, and each one of the worker don't know which is the other one. So there is a huge amount of opportunities in terms of connecting those kind of tasks, make the flow of information very fluid. Then, if you have some specific tasks that are about, I don't know, evaluating physical properties or simulate something and so on, you have a huge space for computational design. So I think that in some way, the opportunities are really endless. And then to all my students that I had through the years, I always thought that don't think about what you're learning in terms of if you want to be a computational designer, don't think about architecture and design as your only opportunities. There are a huge amount of opportunities in biology, in synthetic biology, in any kind of sector, in automotive, whatever it is. There are a lot of opportunities because the ability to define and set and embed information in our tool of production are needed. So it's very different if you just take a downloaded object, you place it in your slicing software and you put in the 3D printer, from having your own object, creating your own tool that doesn't need the 3D object in itself, but deliver the information in the same way to the machine. And if you know how to do that, basically you have the control of the machine because you're owning the language. And so you can play with the machine at a completely different level. So there are huge amount of opportunities, I feel, literally, in the industry. The problem is that we are not really well connected with the industry. I would say that in the last 40 years, especially, more or less all the academy started to disconnect heavily from the industry. And this is something that wasn't that common before, but obviously we didn't have the industry that we have today, but we are on two different planets. For instance, I'm doing some consultancies with very pragmatic robotics companies, and they have to do the job. That's the job that you have to do. So you don't have to invent that much. But the skills that we develop in these 3 years of research about the ability to control the robot in a very precise way, developing our own software, are making the difference, because some tasks are very hard to be done, and you need a very high qualified people in order to do this kind of things, and you can't pay those people all the year. So maybe you need just for some specific task, and that's those are opportunities. So I think that I don't want to say it's easy, but if you find the right company and the right industries where those kind of things are appreciated and paid well, because obviously you don't want to work for free, you have a huge amount of opportunities, because you can bring them something that is new and can make the difference and over the competitors. So, for instance, in the last 4 years, 3 years and a half, more or less, I'm working on 4 big consultancies. They are, unfortunately, as I was telling you, all under heavy NDA, but all 3 of them are literally coming from the informed matter research and the experiment that we did, and they are very big. The only one that I could say the topic is with Comau, and we are literally developing a software in order to don't use points and orientation anymore, but use directly the mathematics of the nerves. So This is something that we studied during the inFORMed research matter and that we dig during this collaboration, but literally it's a completely different software, and few robotic companies are thinking about these kind of things. But it's a way to merge directly. Designers are using NURBS curve all the time, and robots eventually they could start to digest in terms of information NURBS, and we are working on that to make the process or the exchange of information seamless.
Very exhaustive answer, really complete. Well, thank you, Andrea. I think we already passed the hour we planned, and
thank you for the opportunity.
I think as there are no other questions, well, it was really interesting. So I hope everyone enjoyed it. And
I did.
With this, we close, and thanks again. Thanks, everyone.
Thank you very much. Bye-bye from Italy.